Welcome everyone. In continuation to the electromagnetic course, today we will be discussing about electromagnetic waves in guided structure called waveguide. We will learn about the point form of Maxwell's equation, wave equations, electric and magnetic field distributions, wave parameters in rectangular waveguides. A waveguide is a special form of transmission line consisting of a hollow metal tube. The tube walls provide distributed inductance, while the empty space between the tube walls provides distributed capacitance. The metal structure behaves like a good conductor, and the empty space may be filled up with a dielectric. Look at the pictures in the slide. You can see rectangular waveguide and circular waveguides. The dimension of a rectangular waveguide is written as A times B. You also can see the field distributions in a rectangular waveguide in this figure. The red arrow shows the electric field and the dotted loops shows the magnetic fields. Wave equations in a rectangular waveguide. Consider an electromagnetic wave propagating in the positive z direction. In order to determine the field configurations inside the rectangular guide, Maxwell's equation will be solved subject to the appropriate boundary conditions. In the dielectric, inside the guide, we can write the Maxwell's equation in the point form and frequency domain. Let us assume the dielectric substance is isotropic, linear, homogeneous, source-free and lossy medium. Therefore, the Maxwell's equations will be curl of E equal to negative j omega mu H. Curl of H is equal to sigma times j omega epsilon E, where sigma times j omega epsilon E can be replaced by effective permittivity or complex permittivity, and we can write j omega epsilon E times E. Divergence of E equal to 0, divergence of H equal to 0. Now to derive the wave equations, we can take curl on the first Maxwell's equation. That will gives us curl of E equal to negative j omega mu curl of H. Then we expand the left hand side and replace the right hand side with Maxwell's equation, and finally we will come up with a second order differential equation, that is del square E plus k square E equal to 0, where k is called the wave number and k is equal to omega times square root of mu epsilon E. Similarly, by taking curl on the second Maxwell's equation, we can find wave equation in terms of magnetic field. So that is curl, so del square H plus k square H equal to 0. Please note that we have used frequency domain but dropped the subscript H for convenience, because there will be a lot of wave equations and expressions in waveguide, and we want to write them in simple form. That's why we remove the subscript s. To simplify the wave equations, the del square term can be written as, in Cartesian coordinates, del square E equal to partial square E over partial x square plus partial square E over partial y square plus partial square E over partial z square. It is assumed that the propagation in the z direction, in the positive z direction, and that the variation of all field components in terms of z is expressed in the form e to the power negative gamma z, where gamma equal to alpha plus j beta. Assume as simple as E equal to Ez e to the power negative gamma z. Therefore, partial square Ez over partial x square plus partial square Ez over partial y square plus partial square Ez over partial z square. We write put it, take the derivative 2 times and you will get gamma square Ez plus k square Ez equal to 0. Now gamma square plus k square Ez can be written like AC square Ez, where AC square equal to gamma square plus k square. We can write wave equation in terms of Ez and Az. We already showed you how to find the wave equation in terms of Ez. We also can find the wave equation in terms of Az by following the same steps. So you can see the wave equation of in terms of Ez in the left side, and on the right side you can find the wave equation in terms of Az. So in this case you will see for both cases you will identify that wave has a Ez component, but it is also a function of x and y. Relate the E and A speed component using Maxwell's equation. So we apply the first Maxwell's equation. Curl of E is equal to negative j omega mu s, and then the curl in Cartesian coordinate system can be written like the matrix shown here, and the magnetic field has three components: Hx in the x direction, Hy in the y direction, and Hz in the z direction. Now we expand the matrix and also equate the similar terms. Then we'll get the Ax component as partial Ez over partial y minus partial Ey over partial z is equal to negative j omega mu Hx. Similarly, the Ay component can be obtained from the second equation here, and the Az component can be obtained from the third equation. If we consider the second Maxwell's equation, curl of A is equal to negative j omega epsilon E times E. Then expand the curl expression in terms of magnetic field, and we will come up with the expression shown at the right side of this page. As you know, the variation of the wave in z direction, so therefore we can write E equal to Ez e to the power gamma z. So if you take the derivative in terms of E in the Ez direction, you will get gamma, negative gamma Ez e to the power gamma z. So which implies that if you write d over dz is equal to negative gamma, so we can replace the expression by taking d over dz is equal to negative partial gamma. So then we rewrite the above obtained equation with gamma. So we replace the above obtained equation by replacing partial over partial z with negative gamma, and we will come up with these 6 simplified expressions here. The left side is shown in terms of E field and right hand side is in terms of magnetic field. Now we can minimize the unknown number of unknown quantities. Like for example, we obtained the expression partial over partial y Ez plus gamma Ey is equal to negative j omega mu Hx, and also we obtained negative gamma Hx is equal to partial Hz over partial x equal to j omega epsilon Ey. Now replacing Ey in the in the previous expression, you will get partial over partial y z plus gamma over j omega epsilon E multiplied with negative gamma is Hx minus partial over partial x Az equal to negative j omega mu Hx. Then solve this expression, and finally you will come up with the Hx in terms of Ez and Az. So if you look at the final expression here, you will say Hx is Hx in terms of Ez and Az. We get Hx in terms of Ez and Az. Similarly, if we take other expressions, we can find hy in terms of ez, ex in terms of ez, and ey in terms of ez. So all the field components are obtained in terms of ez and az. So we find the ez expression in terms of the from the wave equation. So that we already showed you how to derive the wave equation in terms of ez. Then we find ex, ey, hx and hy by using the Maxwell's equation. And now if the wave is transverse electromagnetic wave, that means Ez and Az both are 0, so it is not possible for waveguide. In TEM waves we have Ez and Az. Ez and Az both are 0, there is no Z component for TEM waves. But in rectangular waveguide, TEM waves are not possible, because for TEM waves both Ez and Az must be 0. But for transverse magnetic or E waves, we have Az equal to 0, but Ez is not 0. That is called transverse magnetic wave. And for transverse electric wave or H field wave, that is Az not equal to 0, but Ez is 0, that calls transverse electric wave. We could have both Ez or Az, both of them are not equal to 0, that is called hybrid waves or AC waves. So in the rectangular waveguide, we consider either Ez or Az exist. So for transverse magnetic wave, we don't have Ez component. For transverse electric wave, we don't have Az component. So in here we'll discuss about the modes of operation. Look at the figure at the left side, you see that is transverse electromagnetic mode. So here both electric field and magnetic field both are perpendicular to the direction of propagation. So there is no E component for electric field or magnetic field. So electric and magnetic field both are propagating in the Z direction, but they are not they has no component in the Z directions. So as we learned in the previous chapter in transmission line or wave in free space, we found that neither electric field or magnetic field propagates in the varies in the Z direction, but both electric and magnetic field are propagating in the Z direction. They have no component in the Z direction. So that type of wave or those type of wave are called the transverse electromagnetic wave. When an electromagnetic wave propagates down a hollow tube, only one of the fields, either electric or magnetic field, will actually be transverse to the wave directions of travel. The other field will loop longitudinally to the directions of travel, but still be perpendicular to the other field. Whichever field remains transverse to the direction of travel determines whether the wave propagates in TE mode, transverse electric mode, or TM mode, means transverse magnetic mode. So look at the figure at the left bottom corner. The left figure is a transverse electric mode. So here the magnetic field is loop, produce a loop, and electric fields, the lines, the vertical lines, they has the component in the Z direction and also in the X and Y direction, but magnetic field has component in X and Y direction but not in Z direction. Similarly for TM modes, you see the electric field makes loops, but the magnetic field propagates in the Z direction. So magnetic field has component in X, Y and Z, but electric field has component only in X and Y but not in Z. That's why it is TM mode, and the other figure shows TE mode expressions. Now for TM waves, we know the wave equations gives us the expression in terms of Ez, Then we find the x and y component for magnetic field and electric field, as Hz is 0 for transverse magnetic field. So we can find the modified H and modified x and y component for both electric and magnetic field expressions. So look at the expression, final expressions here. You can see the x and y components has only a function of Ez. Now we solve the wave equation in terms of Ez. Let's assume Ez varies in x and y and propagating in z direction, and also consider that h square equal to kx square plus ky square. Now the Ez has function of x and y and that propagating in the z direction. So we assume that Ez equal to x times y times e to the power negative gamma z. Now we use the separation of variables rule, and we can write the x variation plus kx square x equal to 0 and the y variation partial over partial y square times y ky square y equal to 0. So now the solution to the x will be x equal to a1 cosine kxx plus a2 sine kxx, and the solution of y will be a3 cosine kyy plus a4 sine kyy. Now the complete solution of Ez will be a1 cosine kxx plus a2 sine kxx and also a3 cosine kyy plus a4 sine kyy e to the power negative gamma z. We apply the boundary conditions like Ez equal to 0 at y equal to 0 at y equal to b. So if you put y equal to 0, y equal to b at the boundary in the metal, inside the metal there will be no electric field. So put Ez equal to 0 and also y equal to 0 and y equal to b. If you put y equal to 0, then you will come up with a3 equal to 0, and if you put y equal to b, then you will find sine kyb equal to 0 and sine kyb equal to 0 when sine is equal to n pi. We can find ky equal to n pi over b, where n is equal to 0, 1, 2, 3 like this. We also can take another boundary equation like at x equal to 0 and at x equal to b, the y component of electric field, the z component of electric field will be 0. And also by putting this boundary condition, we can find a1 equal to 0 and also sine kxa equal to sine m pi, and where kx will be m pi over a, where m equal to 0, 1, 2, 3 like this. So now we obtained the values for a3, that is equal to 0, a1 equal to 0, kx is equal to m pi over a, and ky equal to n pi over b, and we also find a4 and a2. So we write that a4 and a2 is equal to the magnitude of electric field. So therefore the final expression of electric field is Ez equal to E naught sine m pi over a times x sine n pi over b times y times e to the power negative gamma z. Now the TF wave equations, you already obtained the Ez expression. We apply the expressions we obtained earlier to find Ex, Ey, Hx and Hy. So use those expressions to find the equation for x component of electric field and magnetic field, and also y component of electric field and magnetic field. So now all the electric field and magnetic field equations are here. The Az is equal to 0 because it is TM wave. We repeat the same work for transverse electric field. At transverse electric field, Ez will be 0. So at first we write the wave equation in terms of Az, and then as Ez equal to 0 we can find modified expressions for Hx, Hy, Ex and Ey. Look at the simplified expression on this slide here. Now we solve the transverse electric wave expression. We assume that magnetic field as a function of x, y and propagating in z direction. So Hz is equal to xy e to the power gamma z, and then we write down the variable h square has two component kx square plus ky square. So now we separate the expression in x and y direction and solve them with the separation of variable rule. So then you will come up with the solution for x equal to a1 cosine kx plus a2 sine kxx, and also the solution for y is a3k cosine kyy plus a4 sine kyy. Then the solution for hz will be this one shown here, but in order to apply boundary conditions we need the electric field expressions. So we find the electric field expression Ex and Ey from Hz using the Maxwell's equation we derived before. So now at the boundary Ex will be 0 at y equal to 0 and at y equal to b. So that gives us a4 equal to 0, and also sine kyb equal to sine n pi, that gives us ky equal to n pi over b. Similarly, if we put the boundary condition like x equal to 0 and x equal to a, we will find a2 equal to 0 and kx equal to m pi over a. Therefore, the final solution will be hz equal to h naught cosine m pi over a x cosine n pi over b y e to the power gamma z. Here h naught is nothing but the product of a1 and a3, the arbitrary variables that we have obtained before. So we can assume that the product of a1 and a3 is equal to the magnitude of the magnetic field. Now we see the transverse electric field equations are Hz that we obtained from the solution for wave equation. Then we use the Maxwell's equations to find the Ex and Uy, Hx and Hy. There is no Ez component because it is transverse electric field, so Ez is equal to 0. In the solution to the wave equation, you find the integer number m and n. The integer number in the expression m and n are called the modes of the wave. So for example, if m is equal to 1 and n is equal to 0, the mode is called 1 0. If m is 3 and n equal to 2, that mode is called 3 2 mode. So therefore the value for m and n will be integer, and these integers are indicates the mode number. So for Tm wave 00, Tm 00 or Tm M0 and 0n are not possible, because if you put Tm 00 on value either m or n equal to 0, you will see all the field component goes to 0. All the field components will be 0 if you put either m equal to 0 or n equal to 0. Therefore, the lowest possible mode or dominant mode for Tm is equal to 1 1. So 1 1 is the lowest mode. Dominant mode is the lowest value for m and n is possible for a rectangular waveguide. For Tm mode, the lowest possible value is 1 1. So you can assume m equal to 1 and n equal to 1. That's the lowest value. You cannot assume m equal to 0, n equal to 0, or m equal to 0 or n equal to 0. So no 0 is possible for a Tm modes. For Tm on 0 mode, if you put Tm on 0, means there is no magnetic field, z component of magnetic field. So Tm on 0 has Ez equal to E naught sine m pi over a x times sine n pi over b y times e to the power gamma z. So if you put m equal to 0, then sine 0 will be 0, then Ez becomes 0. Or if you put n equal to 0, you also get Ez equal to 0. Or both m and n are 0, you also get Ez equal to 0. So the equations become invalid for 0, 0. That's why Tm, the lowest mode will be either m and n could be as low as 1, not can be 0. So the lowest value is 1, 1 for Tm mode. But for Te waves, the dominant mode or the lowest possible mode is could be 1, 0 or 0, 0. But Te 0, 0 is not possible, because for Te mode there is no z component, but for Te waves you see has a cosine function. So it is possible from the expression, if you put cosine 0 and cosine uh, cosine m equal to 0, then cosine n equal to 0, then hz becomes a constant function. So you cannot find the other component from a constant, so it is not varying, right? So that's why we cannot put m and n both at 0 for Te mode. But if you put 1 is 0, like m equal to 0, then the wave will be still function of cosine y. So it is possible. And if you put n equal to 0, then the hz will be still function of x. That's also possible. So for Te mode, the lowest mode could be 1, 0 or 0, 1, depending on the dimension of the waveguide, but 0, 0 is not possible. So for both Te and Tm wave, 0, 0 modes are not possible, but for Te wave, 0, 1 or 1, 0 could be possible, but for Tm waves, no component could be 0. So either m or n both should be non-zero.